All right, so let's do example 3. And then again, just going to copy this over. File, save as example 3. Wait, nope. Open example 3. Oh, okay, never mind. All right, I'm just going to delete this. So I've got a clean example 3. I hit F5. I've got nothing. I am going to, real quickly from my example 1, I am going to pull in this first figure because we don't want to rewrite that whole thing again, right? And so example 1, I hit F5. So really, if you just want to save example 1 as example 3, load in your data, you can get that. Okay, so has some sort of plotting error, but we're going to ignore that for right now. I'm going to get rid of all of this extra data, all of this extra labels. You know what? I'm just going to, because we're in a class, this is what I'm going to do. Go ahead and copy in these 3 lines, D, T, T, and AC. So if you can get that, if you can get to that point, then we'll just recreate the figures, because that way we can do it together. All right, so let's go plt.figure. Fig size is equal to 6.5 comma 3. And then I just kind of created a figure. We're going to go plt.plot tt comma ac. plt.grid. True. I just want to have a plot grid. plt.xlabel. Time. Whoop. Units of seconds. plt.ylabel. Acceleration in units of meters per second. $(2) $, close parentheses. There you go. Oh, plt.tight layout. And there's my data, right? So this is the data that comes in. Who knows what an FFT is? Who knows what the frequency domain of a signal is? A couple of people. Who's heard the term frequency? Okay, so frequency domain will give us a way to reproduce our time series data in the frequency domain. I want to do an FFT of this. How can I do an FFT of a signal without using ChatGPT? Think about the old days when you just had Google, right? So if I want to do an FFT, I might say, go to Google, and say FFT in Python example. Now, I see a couple different places. I have Python read the docs, but I don't want to do an FFT in pure Python. So I come down here to the third one, Fourier transforms, SciPy.fft. Because I'm doing signal processing in SciPy, and I know that SciPy is a good way to do signal processing, I'm just going to go ahead and click on this one. And it has this wonderful little example, kind of walks you through the math of this FFT. Granted, we could read the documentation and build up a plot from scratch. That's a wonderful way to do it, but let's be honest, this is how most people are going to do it. We're going to copy this code in, and we're going to merge this code into our problem. How does that sound? Pretty good? So first of all, I'm just going to copy all of this code. Control-C, like a real computer scientist. Control-V. Welcome to the club. some reason it gave me a lot of extra line gaps. I'm going to hit F5. Now we're going to hit our first problem. What's going on here? Why do I have 2 lines? Anyone want to take a stab at that? Because I'm plotting 2 lines, but why are they not like, yeah, because I'm plotting 2 lines. That's very nice. Okay. It's because even though I have a PLT dot down here, I haven't created a new figure environment, right? Your first figure environment, Python will give you for free. So in the example, if you don't call a figure environment, it says, oh, no figure environment's open, I'll create one. But if one's already created, it's just going to throw this FFT onto that plot, which isn't really what I want. So I'm going to come up here, and I'm going to go plt.figure, open and close, and hit F5. And now I've created a new figure. I have an FFT. How cool is that? So now I want to do this math on this signal. Does that make sense? So let's just start merging. First thing I notice is from SciPy FFT, import FFT, FFT freak. So that's fine, but I don't want it down here, right? I want it up with my other ones. I'm just going to copy and paste. And then import NumPy as NP. I already have that, right? I don't need it. As we delete code, we hit F5. We're constantly running our code just to make sure that it's still executing without errors, right? So we know when we delete something of importance. All right, this is not a signal processing class, so we're not going to go too deep into it. But the number of sample points of n is 600. How many sample points are in my data set that I care about? How can I find out? Layton, how do I figure out how many data points are in my acceleration data? How am I going to count them? All right, so let's come up here and look at AC 1,177,599, right? So I can do that. I can just type that in, 1177599. Is that a good idea? Probably not, because I can miss something, right? So how about I just go AC.shape, open and close curly brackets, open a square bracket, hit 0, and that'll give me the first dimension of my array. That will not. Maybe there might not be curly brackets. There you go. So now I just program it in. So I don't actually have to know my n. I just say, find me the length or the shape of the first dimension of AC. Does that make sense? All right, now what's T? It's my sample spacing. What do we call that? In time step, yep. So they have 1 over 800, 0.00125. How can I find my time step for my data? Where is my time scored? In lowercase tt, right? I just want to know the difference between tt of 1 minus tt of 0, right? That gives me my time step. Yeah, it might be better. Oh, but let's say you're not just running a bad code, right? So I wrote this LabVIEW code, and I know that LabVIEW takes in data as fast as it can. It doesn't mean that every time step is going to be exactly right. This code's very close. It doesn't matter. But maybe you have a less decent accurate, and you just want to get the average time step, right? Good way to do that might be to go tt of your last data point. In Python, how do you get to your last data point? You can do -1, because in an array in memory says, well, if I'm at 0, what's -1? It just takes me to the top of my stack, right? So -1, tt of -1 gets me 45 seconds minus tt of 0. I don't know what 0 is actually in this. Oh, just happens to be 0. But sometimes your time doesn't start at 0, right? Now I just want to get the average. So I have that many data points divided by, we're just going to go divide by n, right? That should get me my time step. Those are very different. What did I do wrong? I actually don't think that's wrong. I don't think that's wrong, actually. I think that might be right. 1 divided by t, 13. Nope. What did I do wrong? Samples. So samples per second. Well, right now I am not sure, but that's not the number I want. I'm going to go TT of 1 minus TT of 0. Maybe I've got an extra T value. I'd have to dig into it more. I'm not that worried about it right now. So I have 0.00003906 is my time step, which then if I want to find my sample rate, I can do 1 divided by T, capital T, and my sample rate is 25,600, which is correct because that's the sample rate of the module that we used, right? So again, it's kind of helpful if you understand what your data actually means. I'm sampling my signal at 25,000 samples per second. So good, that's what it's coming out as. All right, it has my X data. So this line is creating my X data. For my plot, what is my X data? What's the X data for our acceleration plot? Time. Yep. So how about, just so we don't have to redo all of this, I'm just going to go x equals tt. Just going to redefine it. Is it good code? No. But we're just trying to get our FFT to work. Y, it creates a couple sinusoids here to take an FFT, but that's like synthetic data. And my Y data is just going to be AC. YF of FFT of Y. Okay, so that's fine. X of F equals FFT freq of n comma 2 all the way up to n divided by 2 because I'm just taking the right-hand side of my FFT. Import Matplotlib as PyPlot. Well, I already have that up above, and I should be able to do this now. And okay, now I get a second plot that is the FFT of my signal. And I am going to spend a little bit of quick time now cleaning this up. I don't need plt.show because whenever Python automatically shows it, that's for like if you're working in a terminal. And I'm going to just copy in my X and Y labels. What's my X domain now? Frequency in hertz. It's just an FFT, but I'm just going to put power. We're not going to worry about the units of an FFT, particularly in this class. And then there's my FFT. Now, you might only be worried about this part of the FFT, right? Because the beam only, you just say anything above 100 hertz, I don't care about, right? All right, what do we see here in this beam data? Anyone want to take a stab at it? kind of what do we see in this beam data? Yeah, we kind of, well, that's a great question. Why do we think we see this jump here? Anyone want to take a stab at that one? Remember that we took an FFT over our entire system. How many system states do we have for that? 1, 2, 2, because the mass drops, right? So what we're seeing here possibly is the FFT of the system with the mass attached, the first mode, and then the frequency response of the system with the mass detached on the second mode, right? So we may want to, you could like, here, let's do this. Let's see, at about 20 seconds, right, our mass drops. So if I go to my variable explorer, if I go to time and I drag this out, we got to find where 20 seconds happens. There's definitely more efficient ways to do this, but that's okay. Just shake the mouse. About 500,000, that's my guess. Perfect, 500,000. So at about 500,000 data points. So instead of taking all of my data in my column, I'm going to go from 0 to 500,000 and 0 to 500,000. And now I just have an FFT of the first half of my signal. And let's see, oh, good. Like maybe it's gone. And now we just have 1 bump instead of 2 bumps. Does that make sense? That's a big chunk of your first assignment, right? Is saying, so what you might want to do in your first assignment is say, here's an FFT of the first half of my signal. Here's an FFT of the second half of my signal. I have some sort of model, and I have a rules-based approach where I find the peak of that system, and that becomes my natural frequency, and I divide by that to get K. Right? Again, just 2 pages, super simple. The goal of the first homework is for you to realize that you can explicitly program systems to learn, right? Or you can explicitly program systems to follow. And then we're going to slowly replace that set of skills with the machine learning set of skills. Okay, I want to do a spectrogram. This can also be very useful for you in your first project, right? So we're going to plot spectrogram. And I don't pretend that like everything I do here makes perfect sense, but hopefully by you doing it, you can kind of at least get a decent understanding of what's going on. So a spectrogram is like an FFT, but it adds the time dimension back in. So we're going to go plt.figure. Fig size is equal to 6.5, 3. I mean, you could definitely add that later when you put it into your plot. F, T, capital SXX is equal to SP dot signal dot spectrogram, SPECTR TROGRAM. Okay, yeah, it's showing up there. You can also hit enter. I'm just lazy. And we're going to go X, comma. Now, FS is my, if I hit this, if I click on spectrogram, I should be able to hit Control I. There you go. Then you can actually see what everything is here. F of S is sampling frequency at time of the X time series, defaults to 1. But we don't have a sampling frequency of 1. We have a sampling frequency of 25,000. So I'm just going to copy this variable, sample rate. That'll give me that. Now I need a window. Default is Tukey 25. So sure. if you say so. Let's do that. 2 key as a string, comma, 0.25 is the default. So we'll just put that in there for now, and that's fine. We'll adjust it later. Actually, let's see. Let's see if this actually works as it is. It might. I'm not really sure. Okay, I have no figure yet because I've just computed the spectrogram. SciPlot doesn't do plotting. And so now I want to plot the spectrogram. So again, plt.pcolor mesh t f sxx see if that works. There we go. I got a spectrogram. From 0 to 12,500. It's a vibrating beam. I probably don't care about my frequencies that high. Well, first, those are frequencies, right? So probably a good thing. Let's add some X and Y labels here. So except now the Y label is frequency. And the X label is time. Okay, so I got frequency. Oh, I'm off my plot. So let's add the tight layout. PLT dot tight layout. All right. So everything I'm interested in is going to be way down here with this yellow line, right? So I'm just going to set my y-lim, plt.ylim from as a list from 0 to, what do we want? 100 maybe? You know, that might give me most of what I'm interested in. Ooh, okay. Look at that beautiful plot. I got it. Yeah, garbage in, garbage out. Okay, I've got X here, which is a wonderful variable. But up here, I defined X as TT. That's what a spectrogram of a linear line looks like. That's not what we want. How about we just throw some AC into that and see what it looks like. That is why you don't change the variables in the notes. Oh, look at that beautiful spectrogram. All right. If we increase our number per segment, then we should get a finer resolution in the Y, right? So right now I'm at 5,000, and if I go to 50,000, I should get a finer resolution in the Y, but that comes at a cost of some other things. But that looks pretty cool. So this is before my mass drop. This is after my mass drop. What you'll notice is my second frequency before my mass drop has a big change in frequency to after the mass drop, right?